Okay, so now it's recording. So let's start with the class today. So I'm gonna change now position. Yeah, good. So is everything okay? Can you see it? Okay. So the first chapter is gonna be a more a mathematical chapter. This is called order theory. So this chapter is about really trying to learn more math that is useful to us for this particular class. So you're not gonna see this with Maria. And for me, it's just as a handout. This is something that will help you through the class. I'm not gonna test you on this, okay? So just full disclosure, this part is more about trying to develop some tools, almost like a dictionary for understanding some of the things I'm gonna say. So I'm not gonna test you on this. There is nothing really hard about this. It's just definitions and a lot of notation, okay? So in that sense, this is a hard and dry class, but it's actually important for us to develop some language, okay? So we have the same language to be able to proceed. Agree? Okay. So order theory. What is order theory? Okay, so this part, as you see, I'm just gonna try to explain you and give you additional comments. But in particular, I typed these notes with the main content I think you should know if you're reading. But of course, in the class, I'm gonna tell you way more information. So in particular, order theory is pretty much a part of mathematics that is essential to understand some decision theoretical aspects of consumer theory. So that's going to be an important part of the language of decision theory. So decision theory is pretty much a social science at this stage, right? It's part of econ. But the language that it uses is a lot of order theory, which is a mathematical object. So you just need to understand this math language in order to understand some of the modeling of consumer behavior, right? So this is two layers. As economists, we care about describing consumers, right? And then we use mathematical language to be able to do so. I can describe it with words, of course, but I'm gonna be more precise and it's gonna be more economical if I describe this behavior using a precise mathematical language, which in particular in this case is order theory. So order theory, of course, goes beyond that, beyond decision theory, but we're gonna learn today more the mathematical part, okay? So what is the main object of interest? It's called a binary relation, okay? So now I'm gonna give you a lot of notation, then explain how it links to econ. So let's start with some set, capital X. You can imagine this set that it can be, for instance, a set of alternatives. So imagine I want to model the behavior of consumers that are trying to buy a new car in London, Ontario, right? So then what is X is gonna be the choice set. So this is the collection of all possible cars that a person can buy in London, Ontario, okay? So this set has, for instance, all Honda models or all Ford models and any brand that is sold here, okay? So you can imagine this set to be this exhaustive collection of all possible cars, new cars that a person can buy in London, Ontario in 2020, okay? So this is an example of a set. It can be anything else. Right now it's super abstract. And then we're gonna define an object on this set that is gonna capture what, for us, our purposes, a preference relation. But right now it's gonna be a super general relation, mathematical object, and it's called a binary relation on X. Okay, and what is a binary relation on X? It's basically a subset. So this is gonna be called by uppercase R, which is the sign for relation. And what is a relation? A relation is a subset of the product space of X times X. So what is a product space? What is a product set? A product set is basically I take any item in X and then I pair it with any other item in X. For instance, now I'm gonna have ordered pairs of Honda with Ford, right? Honda CRV with Ford something, okay? So these are all ordered collections. And then in particular, I'm gonna say that if the ordered pair X comma Y is in the relation, then I'm gonna say that X is in relation with Y, okay? And the notation is like this, X super R Y. And if I say, for instance, X is in relation with Y and Y is in relation with Z, that means that at the same time, X is in relation with Y and Y is in relation with Z, okay? So in shortcut, we're gonna write this R in between, the relation between two items of X, as this ordered pair. So short story, for the rest of the class, we're not gonna use the ordered pair notation, okay? We're gonna use this item relation symbol, item 2, okay? And then if we want to link many ordered pairs, we can link them in a chain, right? So X is in relation with Y, and Y is in relation with Z. Understand? This is just notation, okay? So all of these objects are ordered pairs. Now, why do we care? So in particular, when you go to chapter 4, I'm gonna tell you that we're gonna use these ordered relations in order to model consumer preferences, right? Because I'm gonna tell you that an item X, for instance, a commodity bundle, a basket of goods, is better than other basket of goods. I'm gonna write it using an order relation, a preference relation, right? So being preferred, an item X being preferred to an item Y is an order relation. Do you understand that? So that's gonna be the main way we use it, okay? But this sounds simpler than it is, and we have to actually understand a little bit more things about these order relations, because in particular, when comparing two pairs of goods, I actually may be dealing with different objects. For instance, think about choice, right? What kind of objects do you choose usually? You may be, for instance, if you are interested in finance, you are choosing between portfolios, right? What is a portfolio? It's basically a lottery, okay? So a lottery, how do you describe mathematically a lottery? Well, you have to say the states of the world, right? So you make a profit, you lose everything, the probability of each state of the world, right? 50-50, and then the money you will make in each state of the world, right? So that's a complex object, a mathematical object. And then I have to be able to compare two portfolios. How do I do it, right? So I have to understand now the structure of these lotteries. Imagine you have a basket of goods. A basket of goods is going to be a vector in R, L being the number of goods. So just a vector, right, with many entries. And then each entry is going to tell you the amount of units you have of each good. Now, how do you compare two baskets of goods? Well, now you're comparing vectors, right? So it's important we understand that this ordering can be put in sets that have different structures. And we have to understand the particularities of this structure when we fix a model, right? So now we're being super general, but I tried you to link to these more precise objects, right, that we're going to use. So you know this is useful, okay? So now...
I have a quick question.
Sure.
So the XY belongs to R and a YZ in relation to, so can we say X and Z are in the relation as well for this case, or it's not necessarily the case?
Okay, good question, right? So I'm going to rephrase it. So if I have this notation here, X is in relation with Y, and Y is in relation with Z, can I infer that X is in relation with Z? Well, not generally, right? This will be called a transitive closure. So what it means is if you have a relation that is transitive, the fact that you have X in relation with Y and Y in relation with Z will imply that X is in relation with Z, right? So only for transitive relations, you will have this to be true. In general, it's not the case, right? So the answer is not in general, but for the models we're going to study, usually it's true because the relations are transitive, right? And I'm going to explain why we need that and so on. So good question. Okay.
Thank you.
Okay, so first example, just from math. So imagine I'm just choosing among money, right? So the choice environment is just money, right? I'm going to tell you, do you like more money to less? And do you like, for instance, $10 to $5? What do you like more? So I'm going to say, look, for this kind of object or set, it's kind of natural to assume that the preference relation really corresponds to the order on the reals relation. Okay, do you understand? So think about money. So what most people like more money to less, right? So you'll think it's actually reasonable to just say the order in this particular space, which is just the reals, money, right, is the greater than equal order. Okay?
Victor, I had a question.
Sure.
So should it be R positive, real number, because we're talking about money, so should it be R positive or just
yes, I mean, that can be a special case, but in this particular example, you can owe money, right? So now you owe me, right? So in this particular case, it's anything, but yeah. the example goes through for positive cases, right? I agree. So now, some important things about this order. This is a kind of nice order because I'm going to ask you the following. So if I take any two numbers in the real line, can you tell me which one is bigger? It's super obvious, right? Yes. You already make it. You already know it. It's almost a second nature. You even think the question I asked was weird, right? Because you already know this order is complete. This is a complete order, right? So not all orders are complete, and I'm gonna give you examples. But one important feature of this order on money, on reals, is that this order is complete. I can take any two quantities and they are always ordered. I can always tell which one is above the other, okay? Now, second thing is about transitivity, right? So for instance, if I have that you like $10, right, to $5, and you like $5 to $2, then it implies actually that you like $10 to $2, right? Because this order is also transitive. So this order is special in the sense that this is complete and transitive, right? So it's a complete and transitive order, okay? And this is gonna have a special place in our study of decision theory because it turns out that economists call orders that are complete and transitive rational orders. Rational as in a rational being, right? So that's our way to model intelligent decision making, okay? Complete and transitive orders. For money, it's trivial, right? So you like more money to less, that's it, right? But now we're gonna see things get complicated as we study more complex objects, okay? So next example is R2. So now I'm gonna tell you, look, this is a portfolio, right? For instance, imagine that I have two states of the world. So one is the state of the world business as usual. The other is it's gonna rain, right? So the one is sunny, first entry, the other is rainy, okay? And now if it's sunny, you're gonna get this amount of money, one, and it's rainy, you're gonna get $2, right? So this is a weird object, but this is gonna pay you $1 in a state of the world one and $2 in the other state of the world, right? At this stage, you don't know the probabilities of this state of the world, so I'm just gonna give you these two quantities, these monetary amounts in these two states of the world. And I'm gonna tell you, look, imagine just for simplicity that the states of the world are equal probability, right? So you don't care about the probability of it for simplicity at this stage. And I just want to ask you, how can you, when is a portfolio that is a vector of size 2 better than another portfolio? So in particular, take two objects of X, A and B, same as before, but now they are vectors of size 2. And then now the question gets hard, right? Because you will realize quickly that there is no single way of ordering these things. Do you agree? So for instance, I'm gonna tell you in a second, so I'm gonna move a little bit to this particular example. So for instance, imagine that I have these particular two vectors, 1, 2, and 2, 1. So which one do you like? Given that the states of the world are the same, 50-50. So anyone has an opinion? Which one do you like and why? So the vector 1, 2, 2, 1. The first vector gives you $1 in sunny. The second vector gives you $2 in sunny, and the other gives you 2 in rainy, 1 in rainy. Which one do you like?
It should be indifferent, right?
Why? Just tell me your reason. There is no correct answer, so yeah, you can tell me your reason.
The expected value is the same, right? For both, right?
Yeah, that's one way to do it, right? And that's actually very cool because what you did is say, look, I cannot rank vectors, right? Because vectors are size 2, and usually rankings here in vectors are complicated. So one way to rank them, for instance, is by means of expected utility, right? So I just make it into a scalar. So you're going back to the reals, right? And then, expected value is something that lives in the real line, so it's already a scalar, and therefore orders in the scalar line is complete and transitive, right? So the expected value ordering is a rational order, right? And yeah, that's a perfectly nice way to do it. Now, what about this other one, right? So I'm gonna do what is called a lexicographic ordering. And in this particular case, I'm gonna say, look, the way I'm gonna order this is by pretty much this person only cares about the sunny state of the world, right? And in particular, the order is gonna say that A is better than B whenever the first entry of A is strictly better than the entry of the second vector, the first entry. So I only care about sunny first, okay? And then only if sunny is tied, so you get the same money for that state of the world, then I consider the second state of the world, okay? And then I consider rainy because sunny is the same, so now I will consider rainy. So this is another way to rank them, and this is called a lexicographic ranking, okay? And this happens whenever the consumer has some sort of strong opinion over which states of the world are important and which goods are more important, right? So in particular, right, you can think of this needs pyramid, right? So for instance, if, say you are back to the cave times, right? So you're a caveman, and they say, oh, would you like food? And then, you know, shelter, and then something like that, right? So first I want to eat, then I want shelter, something like that. So you can imagine any situation where this works. This is another perfectly reasonable way to think about ranking vectors. And notice that this one here is actually transitive and complete. So we're gonna prove that at some point. But now I just want you to realize we want to show that this is complete. So the interesting thing is about that vectors like 1 and 2 and 2 and 1. Previously, they didn't have natural order, but now they have a particular order called lexicographic, and this lexicographic order actually makes them complete, right? We're gonna start understand completeness. So I'm gonna show, whenever you see WTS, it means I want to show, right? So R is a lexicographic order, a lexicographic order is complete. So what it means to be complete is that either X is in relation with Y or Y is in relation with X. So that's the statement of completeness. So in words, it means that I can rank any two items, okay? Any two items will be put in this relation. So take any two arbitrary vectors, V and W, and now I'm pretty much gonna show you the structure of the logical structure, right? So I'm gonna have that the premise is P, right? That you're lexicographic, and I want to show you pretty much the conclusion is that this is actually a complete order. So it has to be that either V is in relation with W or W is in relation with V. So this part is a little bit more wordy than usually, but what I want to showcase in this particular example is that I'm gonna try to be super formal to show something very simple, just that you see the structure of a logical proof. So not all of you have a lot of experience trying to write proofs. So my idea is to give you a hint of how to do it, right, for the people that haven't. So any proof is just trying to verify a logical statement, right? And most proofs are of the form a premise, a logical premise, which is a statement. Like if my lexicographic preferences, my preferences are lexicographic, this is a premise P, they imply something. In this case, the relation is complete. So what is the premise? The relations are lexicographic. What is the conclusion? The relation is complete, okay? And now I'm gonna try to prove it. So in order to prove it, I'm gonna just use the full language, the full mathematical description of lexicographic. So what it means to be lexicographic? It means that if I take any two vectors, right, I have that two things can happen. So V1 is greater than equal to W1, or W1 can be greater than equal to V1. And then another thing that can happen is, of course, that the second entry, they can also be ranked either way. So what I'm saying at this stage is that entry by entry, there is a scalar order. So the first order that we noticed was complete already. And now the main part of the proof is going to show that that completeness entry by entry will carry on through the lexicographic order to the vector orders, right? And therefore ranking any two vectors. So what is the conclusion is that either V is in relation with W or W is in relation with V. So this is the symbol of equivalence, right? If and only if. So V is in relation with W by the lexicographic order just means that V1 is strictly than W1, or the first entry are equal, and then the second entries are order V2 greater than equal than W2. And then the second one is analogous, and this means that now W has the bigger first entry, or when the first entry is equal, the second entry W2 is greater than equal than V2. Okay? So, so in order to prove this, right, how can I proceed? So one of the key techniques to prove things is by trying to prove by contradiction, right? So who can tell me a quick, if you want to try it, a quick verbal proof of this? So how will you go to prove towards contradiction, using the contradiction technique here? So anyone wants to give it a try? Maybe Kursana wants to give it a try. No? Okay, so let's do this. So contradiction is very simple, right? So I want to negate this statement, okay? So P implies Q. What it means, right? So one thing I want you to kind of see from Wikipedia, and you're going to use it many times, is that P implies Q means actually that not P, right? Not P or Q, right? So this is the logical statement. Now, what I'm going to do is try to prove by contradiction, which means that I'm going to negate this, right? So what it means is that I'm going to have that, I'm going to have not P, right? And Q is going to be the object that I want to negate, right? So it's going to happen that at the same time, the premise is false, but Q happens anyway, right? So in other words, you're going to have that completeness here will hold while P is false. So you're not lexicographic, right? Okay. So I'm going to pretty much try to prove there is a contradiction to it. So in particular, right, we're going to do the proof as follows. Let me close something here. Windows. Okay. So let's say that, for instance, you are complete. And at the same time, okay, I see my connections unstable. Are we able to see everything without issues? Okay, good. So this is the first way to do it, so which is not P and Q. The second way to do it is, for instance, what is called the contrapositive. So that means that I'm going to show that not Q implies not P, okay? That's the contrapositive. And another is pretty much by deduction, right? You can also do kind of a step-by-step checking all cases. That's called exhaustive proof. I'm not going to cover it now. So let's do the first one, right? So in particular, my premise is that you are lexicographic. And in particular, I have this ranking by the reals. Okay, so if I want to show that not P, so I'm going to erase this part, not P and Q. That means basically that I have that this doesn't happen, the premise doesn't happen. So, and at the same time, I have that this happens, right? So either P is in relation with W or W is in relation with V, okay? But so let's analyze this object, right? So if any of these two happens, right? The second part here, in the conclusion, then it has to be by definition of the lexicographic, right? That either, right, in the first case, V1 is in relation with W1, right? Or V1 is equal to W1, right? And then we know also that this implies here that V2, but right now I don't care much about the second entry. So this part I just put in parentheses, right? Which this part I'm gonna just collapse to one single object, right? Which is the equality. Okay, so I know that either this happens, right? This part I don't need, so I'm just gonna erase it for now. Or this happens, right? So either of the two happens, right? So if this object here is pretty much the definition of completeness, right? As I shrink it to the particular interest of my proof, then this implies, right, that pretty much B1 is in relation with W1 or the opposite. But I said that this cannot happen, right? In the statement of the negation of the statement, I said this is not true, right? But this is a contradiction of not P, right? The negation of P. So in this case, the proof is so simple that writing it formally, it actually looks weird. But what I did is a formal proof, right? So I basically took two statements, I broke it into the definitions, and then I wrote the formal statement, which is not P and Q. Completeness of Q basically means that entry by entry, you have to be complete, right? But then it means that by definition, right, I'm telling you that the scalar order is not complete, right? So this is a contradiction, basically, of the order in the reals being complete. So this second part is negating that the order on the reals is complete, right? So which cannot be true for sure. So this is a proof by contradiction, okay? So yeah, so this is, I'm gonna do more complex proofs, but this in particular, I'm just showing you the structure, right? So in order to show an implication, I can do just a negation by contradiction, not P and Q, and then I'm gonna go forward and derive a contradiction, okay? Now, let's study another ranking, yet another one in R2. And this is the example number 3, which is for still vectors of size 2. And now instead of the lexicographic order, I'm gonna present to you an order that is transitive but not complete. So the key, the highlight of this ordering is that this is not complete, okay? So some vectors are left unordered, okay? That's interesting. In particular, I'm gonna say that I declare A in relation with B whenever the entry by entry, the entries of the first vector are greater than or equal to the entries of the second vector, okay? So in particular, I want to show that this order, which is called the canonical order of vectors. Why is canonical? Because that's the main ordering people use in vectors, right? And this is called the vector order, okay? This one is not complete. So what it means to be an incomplete order, it means that a pair of vectors, there exists a pair of vectors that are not ranked, okay? So in particular, why do we care about this? So this is actually very interesting because it means that it allows you to model some consumers that they don't know what they like, right? So for instance, if I tell you, do you like a Hyundai versus Mitsubishi? Some people may not care, right? So you say, I don't really know. You see? So that's a case of incomplete preferences, right? So you don't really know which do you like, okay? So now in this particular ranking, I want to show that the canonical vector order is not complete. So how do you show this particular thing? When you have a statement that is a negative statement, so you say, something is not a property, you can just show it by creating an example, right? So in particular, you want to show that there is a particular set of a particular collection of vectors that cannot be ranked by the order. Why can I do it by example? Because completeness is stated as a universal statement, right? So what it means is I say, look, for any two vectors, I can put them in relation with the other. Either the first vector is better than the second vector, or the second vector is better than the first. So this is a universal statement. Any two vectors can be ranked. So how do I disprove a universal statement? By creating an example, okay? So this is the typical example. You say, all swans are white, right? So how do you disprove that? You just need to find a black swan, right? That's it. This is the same thing. You're looking for the black swan, okay? So how do you prove it? Well, I already did the proof here. Is I take a collection of vectors out of my mind, my imagination, right? Here is very simple. 1, 2, and 2, 1, right? Are these ranked in the order? Well, not really, right? Because 1 is smaller than 2, but then 2 is greater than 1. So according to this entry by entry ordering, these two vectors are not ranked. Do you understand? Okay. But this doesn't mean that some vectors are ranked, of course. For instance, the vector 1, 1 and the vector 2, 2 are ranked. Okay. So now we have seen three possible ways of ranking this vector. So Schumann told us the expected value, right? That's one way to do it. That's a complete and transitive order. I told you the lexicographic order, complete and transitive, right? And I told you another order, which is transitive, which I'm gonna show you to one of you to kind of tell me why it's transitive, but it's not complete, right? Okay, so let's go to that particular question. So let me see I'm gonna make this screen bigger to see you all, participants. Okay, so let's try with Tyler. Okay, so Tyler.
Yeah.
Okay, so in example 3 in the notes, you have this canonical ordering of vectors, right? I said that this ranking is transitive, okay? So the definition of a transitive order is that whenever you have vector v in relation with vector w, and vector w in relation with a third vector, call it z, then this implies that the first vector, v, is in relation with the last vector, z, right? So, okay, so I want you to, first of all, tell me a quick sketch of how will you show that this thing is this order, the canonical order on the vectors is transitive, right? So what do you want to show? So I'm gonna help you, right? Yeah. So you want to show that, what is the statement you want to show? You want to say that this ranking, right, define it as entry by entry, you are greater than equal than the other entry. This is transitive, right? So what is transitivity? The premise of transitivity is that two things happen, right? Let's write it down. Let's go to the blackboard, right? I'm gonna do a new page. Okay. So let me do a new page. Okay, so let's start here. So you start with a vector x1, right? x2. Okay? And this vector here, I'm going to tell you that it's in relation with another vector called y, right? y1, y2. And the second piece of information is that now y1 is also in relation with a third vector called z, right?
So I'm now seeing the Blackboard that you mentioned. I don't.
You have a link.
Link.
I'm gonna share.
The link. Oh, okay, link.
Yeah,
Okay.
I will share it now, so you also see it.
Okay.
So in the chat there is a link, right? I guess you can see it now, right? Because I'm sharing it as well.
Yeah. Thank you.
Okay, so you have these two pieces of information, right? X1 is greater than Y1. Sorry, yeah, and X2 is greater than equal than Y2, entry by entry. And also that Y1 is greater than equal than Z1, and Y2 is greater than equal than Z2. Okay? This is the premise. What is the conclusion I want to prove?
The conclusion would be that the vector x is related to z, or greater than or equal to
Okay,
z.
so very easy, right? What do we know? We know that the scalar order, entry by entry, is two things, complete and transitive, right? Entry by entry.
Yes.
Do you agree?
Yes.
Okay, so now we're going to use that fact that we know, right, to show what you just said, that the vector order that is derived from the entry by entry order is already transitive, right? So pretty much that's the way to prove it. So back to Tyler, right? So the idea is that how do I prove this? So I have this my premise, right? And I want to conclude that X is in relation with Z.
Mm-hmm.
Okay? So how do I do it? I know something, that the entry by entry order on the reals, right? Not on the vectors, on the reals is complete, is transitive, it's transitive. So I know in particular that if X1 is greater than equal than Y1, right? And Y1 is greater than equal than Z1, by the transitivity of the scalar order, it has to be what?
X1 has to be greater than or equal to Z1.
Great. And the second piece of information you need is the second entry, right?
Oh yeah, X2 is greater than or equal to Z2.
That's it, right? So what is the fact here? The fact is that the entry by entry ranking is transitive, right? Therefore, the vector order inherits that, right? So we have just proved it, right? So the proof will be formally, and I'm going to go back to my screen on leaks. So I'm going to now prove that it's transitive. You're back to leaks, right? You can see it. Okay. So we're going to show it's transitive, right? Okay. So we say, look, take any two vectors, X and Y in R2, right? In X, I'm going to call it X, but we know it's R2. And now, what do we do with these vectors? Well, we say that, three vectors, because we're talking about transitivity. And we say if X is in relation with Y and Y is in relation with Z, right? We want to show that X is in relation with Z, okay? So now the proof is the following. We say that if X is in relation with Y, this means that the entry X1 is greater than or equal than Y1, and the entry X2 is greater than or equal than Y2, okay? Second piece of information is that given that Y is in relation with Z, this means that Y1 is greater than or equal than Z1, and Y2 is greater than or equal than Z2, okay? This implies, because the scalar ranking on the reals, right, is transitive, that Entry by entry, x1 is greater than equal, and of course y1 and greater than equal than z1, right? Because of transitivity, this implies that x1 is greater than equal than z1. And the same with the other, right? And similar to and the same happens with the second entry. And we conclude that pretty much x2 is greater than equal than z2, okay? So now this means that the vector x is in relation with y, right? Sorry, in relation with z, which was what I wanted to show, right? So in conclusion, x is in relation with y and y is in relation with z implies x is in relation with z. So I prove transitivity. Okay, that's it. So this is a simple proof, right? We use a fact that pretty much we knew that the scalar ranking was transitive. We're using it to prove that the scalar in the vector is transitive. Okay?
Victor, I have a question.
Sure.
So can you do the proof the other way around? So if you can show like if the vector rankings are transitive, does it also imply the scalar ranking has to be transitive as well?
So let me understand that question.
So like we took like scalars here, like then we went to vector, right? So what if we had the other way around? So we had the vector rankings. Does it imply the scalar rankings as well to be transitive?
Yeah, that's true. So I told you here the piece of information you knew is that the scalar thing was already transitive, right? But so if you knew that this was transitive, you can prove that the entry by entry is transitive as well. Because here the definition is entry by entry. So that will be true, right? So yeah, so the important thing about a proof is like to know what you're supposed to know, what you can assume, right? And then given that assumption, that set of things that you are supposed to know, then you can conclude, right? So you change the information, right? In your case, you said, I stopped knowing that the scalar ranking is transitive. I now know only that the vector order is transitive. Now, so given this new information, I want to conclude the other way. And that's fine, right? That's a perfectly well-posed statement. But yeah, so in this particular case, we had a different premise, okay? So the information I have is different, okay?
Is the transitivity of the entry by entry ordering conditional on the space that the vectors come from? So here it was reals, and we knew that reals and the scalars are transitive. But if the space that the vectors came from, that was not transitive to begin with, we couldn't prove that the ordering is transitive, right?
Great. Yeah, so a vector in general can be a collection of anything, right? So in particular, we have entries that are no longer reals, right?
Mm-hmm.
We have now something like, for instance, apples and maybe, for instance, cars in the first one, car models, and in the second one you have bikes. And therefore, there is not really a ranking, a natural ranking at least, on bikes and on cars, right? Unless you create one. So yeah, in these particular examples, we are studying structures that are very mathematical and very simple. But yeah, when you're modeling decision theory, it's very important to know the space you're working on, right?
Mm-hmm.
So yeah, so this is not general because it depends on the set. So again, that's a great question, Kursana, because actually the correct way about thinking about this is that you have to think of this couple of objects, the set X and the ranking on top of it, right? And these interact. So the set will give you a lot of structure, right? Like the reals and so on. And then, so if you have reals, there is a lot of inherited structure, right? But you can have also abstract objects. And this theory is super general, okay? That's a great question. So now we're gonna go to the kind of a very dictionary part of the class. So I'm just gonna tell you definitions, okay? So it's just definitions. There is nothing really to understand here, but rather just pay attention to the definitions and then we're gonna use them. So it's almost like language class. So this is very similar to if you start learning English, learning French, learning whatever language you want to learn. So you at some point you have to learn vocabulary, right? This is the same, okay? It's vocabulary class now. So you have here the properties of binary relations. So binary relations are too general, right? They can be anything. In particular, right now we are gonna put them some properties. So the first property is called reflexivity, okay? And this is gonna show up many times because it's the most natural property of rankings. Usually we always assume it during our class. And this just says that a relation is reflexive if any item is in relation with itself, okay? So this right now, so what it means first in terms of preferences means that you have an object X, you're kind of indifferent to the same object, right? So now as you can see, these relations actually are capturing at the same time strict preferences and weak preferences, right? So at this stage, we haven't made a difference between them. You understand? So we're gonna make difference between a strict and indifference in a second. But right now, this relation can actually capture both. And when I use my orderings in the previous examples, I was using the symbol greater than equal, greater than or equal to. So that means actually equality and being strictly greater were captured as the same object, right? So these preferences here are in the sense weak. So the first property is telling you that anything, any object is in relation with itself, okay? And this just means that this is a mathematical normalization, right? So you can always put this property, okay? So this is not really behaviorally interesting, but you need to know it.
Can you find any counterexample for this property? Is this possible?
Yeah, I mean, for instance, I'm gonna write a counterexample. Let me do it here. So imagine the following relation that is x, y is in the relation when x is different than y, right? So this particular relation, right, is telling me this is the relation you are different. So x is different from y. That's the name of the relation, right? So the relation is called being different. Okay? That's a relation, right? So you take a pair and you declare them as being different, right? And in fact, this relation is very special because the only thing that is not in the relation is the diagonal, right? The objects that are equal to itself. You see? So this is, if you want, this is a kind of a program, right? That tells you, are these two objects the same? A computer tells you, no, they are different, right? That's an example, okay? That's of course a counterexample of reflexivity. This is not reflexive, okay? So there are such relations, of course, I can build them. But in general, for our class, we're gonna just not use them because they are not that interesting for us, okay? Maybe in other fields, okay? Completeness. Completeness also is called in the literature as totality. So you will read both, complete or total, okay? I'll just tell you the two names we use. And this is very simple. So intuitively, you know that it means you can rank any two objects. Formally, what it means is that you are complete if either x is in relation with a y or y is in relation with x. And this holds for any pair, okay? So this is not a statement that one thing is better than other. It's just telling you that two things, you have to know how to rank them, right? So give me an example, any of you, of something that is incomplete. So we already know one, right? But something more like from real life. Or whatever thing you have found in life, what ranking is incomplete? So anything that you cannot rank completely. Well, this is actually a simpler, maybe it's too simple, that's why you're answering. But so completeness usually, so it's basically, this is a very hard property behaviorally, very simple mathematically, right? So completeness means that it's an statement. It's almost, if I'm modeling an agent, it would be great if this agent can compare any two objects, right? Right. But in real life, there are very few natural complete orders, right? For instance, if you have money, like you say, okay, more is better than less. That's a complete order. That's usually natural. That's transitive. That's great. But if I told you these lotteries as we started, right? Why you use the lexicographic order? Why not the order? Versus think about, this is a very simple example. So think about advantage, right? In the equal sense, like comparative advantage versus absolute advantage, right? So absolute advantage is like the canonical order, right? So you're greater than equal in everything, right? So that's a transitive but incomplete ranking, right? So because you have some people that have comparative advantage, so you are relatively better at something. Like the typical example of Portugal versus the UK in the 19th century, right? So the comparative advantage of Portugal is to make wine, and the particular advantage, the comparative advantage of UK is to make garments, right? So textiles. And you know, there is no country that is better at both. So that's an incomplete order, right? So in particular, absolute advantage is an incomplete order. So some people are really better than the rest, right? These polymaths, they know music, they know math, they know poetry, they are good at sports, right? The majority of us, we are not polymaths and we are good at some things, right? I am good at decision theory. Like most people don't care about decision theory. They are better at music and play soccer, which is way more fun, right? But I'm better at decision theory. That's my comparative advantage, right? That's why I make a living out of it, right? So, but it's not easy to rank them, right? And so that's the point. So that's an example of incomplete ranking. Most rankings in the world are incomplete. So I want to have in mind that completeness is going to be assumed all through the class, but this is a very strong assumption, right? That's the only point here. But you can also, I want to start imagining that you can put anything really in real life as a relation. That's the exercise I want you to make, right now. So let's go to the next one. I already gave you examples, counterexamples of completeness, right? So you have it previously, the canonical order. Symmetry. Okay, symmetry is a very cool property. It's gonna be used a lot because this has to do with indifference, okay, and equivalence. So we say something is symmetric if x is in relation with y. This implies that y is in relation with x, okay? So a classical example is being in a family relation with someone, right? So for instance, imagine that I say these two individuals, individual A and B, are in a family relation, right? So if X is in a family relation with Y, what it implies? That Y is in relation with X, right? Because the family relation is symmetric. So it is a mutual relation, right? You understand? So these two persons are in a symmetric relation, okay? So let's do that example of something that's not symmetric, which is related to the next one. Is, for instance, the relation being father and son, right? Mother and daughter, right? It goes one way, right? So person A is the father of person B, right? So then this implies, of course, that person B is not the father of A, okay? So this is a one-way direction. So this is, of course, a counterexample of symmetry. This is a symmetry. And you can see the definition that if X is in relation with Y, this implies that Y is not in relation with X. Okay?
Victor, can we do like this? So it's like 5 relationship to 3. So it's 5 is bigger than 3, but 3 cannot be bigger than 5. That is similar thing like this here?
Yes. And then, of course, equality will be the symmetric relation, right? So 3 is equal to 3, of course, implies that 3 is equal to 3. But more interesting, for instance, with fractions, you can say 2 is equal to 4 over 2, right? The fraction 4 over 2. So 2 is equal to 4 over 2. That implies that 4 over 2 is equal to 2, right? This is an equivalence relation. And this is symmetric, of course. So asymmetry means that you are one directional. So usually think of asymmetry relations as being directed graphs, right? So you have an arrow, right? So this causes that. This person is a father, a mother of the other. So it's one directional, okay? And for preferences, this is actually strict preferences, right? So for us, asymmetry means that if you strictly prefer a bundle X to a bundle Y, then it cannot be that Y is strictly preferred to X, right? That will be something natural to assume. Now, again, all of these are assumptions that I will impose when I need them. They cannot hold usually simultaneously, right? So all of these are like features I will put to my binary relation when needed. They don't need to hold at the same time. You understand? So for instance, if you have a strict preference relation, it cannot be at the same time asymmetric and symmetric, right? Obviously, if it is asymmetric, it won't be symmetric, right? So these are things I'm gonna call as needed, okay? Antisymmetry. basically means the following. It means that if x is in relation with y and y is in relation with x, it means that x is equal to y. So this is kind of a weakening of asymmetry. Right now, I used to have an example of what is the difference between the two. In this particular case, antisymmetry just will cover the gray. So the example will be this. Asymmetry is the strictly greater symbol, right? And antisymmetric, right, for instance, it will be the greater than equal symbol. For instance, if you have x greater than equal than y, and y greater than equal than x, it of course means that x is equal to than y, okay? So in particular, this will be the difference between the two. The antisymmetry allows for the equivalence relation to be included, if you want, okay? But right now, again, there are definitions. We're gonna use them when needed. The important one, transitivity, is important because that's basically the core, the heart of rational decision making. So I'm going to explain why this is so important, but basically, you know, decision theory philosophers decided that transitivity is the main feature of an intelligent game, okay? And we're going to discuss why. But, you know, this is a philosophical decision, right? I take a stand as a modeler that transitivity is what I call rational. So, you know, philosophers, do we have any philosopher here? I had a philosopher last year, so I'm asking. But, you know, defining what is rational thinking is very hard. Will you agree, right? Well, that's the cool thing about math. So centuries of debate pretty much converge in calling rational to someone that has preferences that can be represented as a order relation that is complete and transitive. That's it. That's a lot of information in two simple properties, right? So what is transitivity? Is that if x is in relation with y, y is in relation, and y is in relation with z, it implies that x is in relation with z, okay? So transitivity is about consistency, right? You say you like apple to oranges and oranges to pineapple, right? Now you must like apples to pineapples. Now, in reality, do people behave like that? What do you think? So that's really the question, right? So you see now where we're going, right? So these are mathematical objects. These are mathematical properties. Why transitivity is so important? Why do you think philosophers decided this is a good property to have in terms of preferences? Why do you think it's natural? Why do you think philosophers thought being rational means being transitive and complete? But transitivity now.
Is it an example of deduction?
Can you explain more, please? Expand.
Well, you deduce, it's kind of using the principle of the proof itself. Like if you know that X is related to Y and Y is related to Z, then you deduce that X is related to Z. I don't know if that's right.
Nice. Yeah, that's actually a very nice explanation. Yeah, because it tells you, look, so human being as a machine, right? You can kind of interpolate your preferences, right? You create this closure, this transitive closure, because you say, look, I like X better than Y, and I like Y better than Z. And it must be that X is better than Z, right? So in a way, the way you think is actually very, very nice, because you're thinking, you know, this person is actually transitive as a consequence of kind of extrapolating, you see? So,
Right.
So you're thinking actually of the formation of preferences, right? But so in reality, I think that's a very good justification, by the way. I think it's very nice. But I think, you know, a lot of modeling is done because of convenience, right? And I want you to notice something, right? What is the best ranking you have seen so far this class? What is the one you think is the simplest, nicer, and so on? You're economists. You are learning in my class that more money is better than less money, right? That's the only thing you're going to learn today. No, but in reality, you know, I'm planning to have recorded laughter just in case you don't laugh. So just kidding. I didn't 90s jokes. But the reality is this, right? So think about this simple ranking. Why is so cool? So we take it for granted, right? But in reals, you can take any two numbers and you know which one is bigger. You know, you can rank all of them, right? So it's a very cool ranking. So anything that lives in a real line is complete and transitive. It's very easy to handle because it's one-dimensional, right? So now we live in the time of machine learning, you know, pretty much data crunching. If you're trying to understand decision, what is the issue about decision making? Is trying to reduce dimensions. What is a decision problem? It's a problem that has many, many dimensions, right? Think about a portfolio when you're doing investment. How many variables, states of the world you have to take into account?
Infinity.
Let's say many, yeah, but yeah, infinity, many dimensions. So you go and try to decide what basket of goods do you buy at the grocery store. How do you decide between a particular, collection of them versus another, right? How do you decide about, many things in life, that have many characteristics, right? Like for instance, doing a PhD in econ, pros, cons, a lot of things, right? It's a vector of information, okay? And then, you want to model these hard decisions. What is the ideal? What will be the ideal way to do it? Well, the ideal way to do it is to take all this huge vector of characteristics, information, and whatever, and make it into a bundle, make it in fact into a single number, right? And that single number is what we are going to call eventually the utility function, the value of any item that you're picking. And what is the key thing about a utility function? So who knows here what is a utility function? So utility function, you might have seen it at some point, right, in Micro one. So it's just a real function that takes some item, any vector of things, for instance, and spits out a number, right? And then when you compare the utility of vector 1 versus the utility of vector 2, then you can tell in numbers which one is higher than the other, okay? So it's really about the utility function, right? So the utility function is this reduction of dimensionality that is so cool that takes any sort of dimensions in your decision problem and projects it into a single scalar object, right? And therefore into the real scalar line. So the whole trick is that whatever problem you give me, I'm gonna make it simple by making it complete and transitive, which translated means that under some regularity conditions, there's gonna be a utility function, right? So the solution for decision theories in econ, at least, has been to simplify choice and to make it into one-dimensional again, okay?
So Victor, so if I give you a relation which is not complete or transitive, you cannot put it into a utility function? That's what you're trying to
Exactly, so if I heard correctly the last part, if I have a relation that is not complete or transitive, then I cannot write a utility function, okay? So that's the whole thing, right? So if you don't have, so all the problems that are too complex for a utility function, are not longer rational. That's an easy way to handle things, right? So anything that is complex is not rational. I just call you not rational. Sounds great, right? So that's the important key. Language is important, and you call this thing rational, but it's really a convenience of modeling. Now, now we're also in the time of artificial intelligence. Do you think there is any benefit to be complete and transitive? Like think about now normatively, right? So you're trying to create a robot, like a robot that purchases something for you, right? Now you know that there are some people in finance that are doing robots that do investments for them, right? So these robots, for instance, some of them you can write a simple robot, like Showman suggested, and this robot will check out expected returns, right? And will choose the one with a higher expected return. That's a complete and transitive robot, right? Do you think that robot will do better with some other robot that uses just the greater than equal vector? For instance, you can have a very conservative robot that only purchases a portfolio that is better in all dimensions in the world, right? Why not, right? You have to, the issue with that robot, the second robot, is that that robot may not make decisions sometimes, right? So you say, oh, what did you do the last month? Well, this robot haven't decided anything yet, right? So it's completely undecisive, you see? So this is an important question I want you to think about through our class, right? Is that we're gonna study this benchmark of very simple one-dimensional decision-making, complete and transitive, right? Understand the math of it, understand the generality of it. But at the same time, I want you to understand that this is just the entry point to a huge literature and really a way to think about things. And I want you to think of this model not really as a description of behavior, which we don't know if it's actually a good description. I think it's a good description in some cases, not in general. but also it actually may be an opening to these ideas about artificial intelligence, right? So there are a lot of people that think that being transitive and complete is actually optimal because it's very efficient, very rapid, very fast. So it's kind of interesting, but the fact that you become transitive and basically complete is actually simplifies decision time, right? So imagine in terms of costs of being undecisive, right? Do you want a robot that never takes decisions, right? Maybe leaving things on the table will be bad for you, right? So think about putting to compete several robots to see which one does better, right? Does the transitive and complete have any advantage? So some evolutionary economists have argued that being transitive and complete actually has an evolutionary advantage. That this is better than just being random, right? That people will do better under certain arguments. So all of this is that you have in your mind that there is a lot of things going on in these simple mathematical properties, but in particular, I want you to now learn the formality of the language, right? And now to finish this dictionary part, I'm gonna finish with acyclicity. And acyclicity is a form of consistency that doesn't require completeness, is more general than transitivity, but has the same flavor. And this is gonna tell you the following, right? I have pretty much that x1 is in relation with x2, and x2 is in relation with x3, and x3 is in relation with so and so, until xn and xn minus 1 is in relation with xn. And if you have that chain of relations, then this implies that x1 must not be equal to xn. So, and basically, and let's think about, for instance, a relation that is cyclic, okay? So friendship, right? So cycle of size 2. So say, for instance, person A is friends with person 2, right? Therefore, person 2 is friends with person 1, right? And in fact, in this chain, the end of the chain is, of course, that x1 is equal to the final link, which is, of course, x1. So what I just described is this thing. So I say x1 is friends with x2, right? And x2 is friends with x1, right? That's a cyclic relation, okay, of size 2, okay? Now, acyclic relations are, in general, they are more general transitivity. And in general, transitive relations are, of course, cyclic, right? But a cyclic relation may not be transitive. And so it's more general. We're going to use it at some point. But in particular, think of them as very closely related, right? So acyclicity just means that you are not creating these loops. So think of a loop, right? We're ruling out loops here. Okay, so now let's go to we have an example about asymmetric relations, and I'm done with that part. Okay, so now this rest of the chapter, I want you to pretty much read it. This is gonna be like your handout for understanding some parts of the class. So I'm not gonna go into the whole chapter trying to understand every single part. We're gonna use it as needed, so you can refer back to it when you need. The only thing I want you to kind of right now focus when reading this thing is the definitions of pre-order, equivalence relation, partial order. These are just when we combine several properties together, we call them a name. In particular, just an example is that we call pre-order something that is reflexive and transitive, right? And you can just read it. As you see, it's just definitions. So I'm gonna stop there. The next part of the class is going to be pretty much trying to understand the transitive closure, and that's the part I'm going to focus now. So I'm going to go to the part of the nodes 1.2 to understand what is called transitive closure, okay? So what is a transitive closure? So I have a big definition here, but I'm going to just tell you what is a transitive closure with a simple example. And then I'm going to go to the definition again. So I'm going to go to example number 8. And I'm gonna start with a simple set of 3 items, A, B, and C, okay? Then I'll give you the following information. I'm gonna tell you A is in relation with B, okay? And nothing more. Now, how can I take this original relation First of all, I'm going to check this relation, the properties of this relation. Okay, so this is a binary relation. It's really, it doesn't have any property at this stage because it's just a single order pair, right? There is nothing more there. Do you understand? So the only object there is an order pair AV, nothing else. What is going on with the rest? Well, the rest are not ranked in this relation, are not in relation to any other thing. For instance, V and C are not related. A and A itself is not related. So you see, this is a very sparse, very empty relation. Okay? However, it's a well-defined binary relation. The operation I'm going to tell you, which is very simple, is called closure. That is transitive closure. So what it means is I'm going to take the original relation and I'm going to create a new relation that is going to preserve the original relation and then make it transitive, adding items to the relation. Okay? So how many ways can I do this? I can do many ways. And in particular, transitive closures are not unique. So the first transitive closure is going to be this. I'm going to take A, and I have to respect the relation that is in the set, right? So A is in relation with B. And now I want to make it transitive, right? So I'm going to make it now in relation with C. And therefore, because it's a transitive closure, it also means that A is in relation with C. Okay? So the first one is just a closure where I'm putting C at the very end. And then I'm pretty much closing the loop, saying A is better than B, B is better than C. Okay? And then A is better than C, strictly. Okay? I call this relation C. So now, this is not the only way I can do it, right? I can create a second relation, C2, that now puts C on top. Okay? Now, C is the best. C is better than A, C is better than B. And there is a third relation that I can call pretty much indifference, where I can put everyone on the same level, right? One thing I want you to understand before going to the particular definition is that what I have done is I have taken the original relation, I can create a new relation. This new relation is preserving the first part of the relation in at least a weaker way. So for instance, if this thing was strictly preferred, now this may be indifferent. So this allows you to create indifferences, right? And the other one is kind of free to move as long as you have transitivity on it. So let's go back to the definition. So this is kind of a long definition. That's why I wanted to go first to the example. But you start with some binary relation and you want to put some property on it. In particular, the property I want here is transitivity. And then I want to create a relation that is, of course, a subset of ordered pairs. And this is going to be called a closure of R if it preserves the original relation, right? So it means that if the original relation means that X is in relation with Y, in the new relation, X has to be in relation with Y as well, okay? And the key thing is that the new relation has to have the property that originally I didn't have, okay? Now, in particular, I can do this in many ways, as I show you. So a single preference relation can have multiple ways to close it as a transitive closure. But which one do I take? I take the smaller one. So I take just the intersection of all possible transitive closures that I created, and I take the smallest one, right? And this is the one I'm going to call in general the transitive closure. So the smallest possible extension, okay? And the smallest means the intersection of it. So in particular, I can do other closures, adding other properties, but now I need a transitive closure. So I'm going to call transitive closure TR, even only if it's a closure of R that satisfies transitivity, okay? And the first fact that I'm going to show you today is that every binary relation R has a transitive closure TR, okay? So let's think about a relation that I told you earlier in the class. So the relation of being, for instance, father and son. So I say person A is in relation with person B as being the father of B. So A is the father of B, okay? And now I have also a third person C that is in the set. And this person is pretty much is the spouse of person A, okay? So my original relation is A is the father of B, right? And then C is a spouse of A. But that's the information I'm giving you. The original relation is the father too, right? Now, tell me a transitive closure. Not the smallest one. I don't want the smallest one. Just tell me one particular transitive closure you can come up with. So maybe Eduardo.
Can you just repeat what you were saying? Like the
Yeah.
first.
So let's start with a relation father-son, right? So person A is the father to person B, and there is a third person in this set. This third person is, say, the spouse of A. Okay. Now the original relation is father to. Okay. That relation is not transitive. It's very incomplete and so on. So I want you to tell me a closure of that relation that is transitive. So a closure, right, has to be a complete relation, right? So it has to relate all of the three elements in set. It has to preserve the original relation, right, in some form, and then also be transitive. So three things, right? Complete, preserve the relation, and be transitive.
So maybe saying like C is the spouse of A, which is the father of B, something like that.
Yeah, but what is a relation? So tell me, these three persons can be in a relation. What relation can you call it? What is a relation that is more general than being father to? That's another thing about it.
Family, maybe?
Parent?
Family, being related, right? Okay. So being a family relationship, do you agree this is a relation that preserves being father to? Yes, right?
Yeah.
In this particular set, is this relation complete? Yes, right? Because I told you the third person is a spouse and there is some sort of family relation with the third person. Even I didn't say so completely, but you can fill in the blanks, right? So this is complete as well. Now, the final thing we have to verify is that whether this family relation, so these two individuals are family related, is actually transitive. So Eduardo, is it this relation, being in a family relationship, transitive?
I want to say yes, but I'm not sure. Like
Prove it. That's the technique, right? So take two individuals in this set of three individuals, right? A and B. So A is in family relation with B, right? And B is a family relation with C in this particular set, right? So then does it mean that the other two people are in a family relation?
Yeah.
Yeah. I mean, here, of course, we're filling a lot in the blanks with what we understand as family relation, but we understand the main idea, right? So that's the idea of a transitive closure, right? So father-son relation is a non-transitive, very empty, very incomplete relation. But you can always close it and you can always take a transitive closure of it. So what is the transitive closure? Is this family relation. It's a bigger thing that preserves the father to son relation, of course, but is more general. It's such generality that it makes everything complete, okay?
Is it kind of like creating a bigger set for the subset?
Yep.
Okay.
Exactly. Now, let's go back to with this I'm finished, let's go back to the board. I'm gonna share it. You can see it also. Okay, so for instance, say I start with this node X, right? And I have a node Y. This is a graph, right? And I have a third node Z, right? So then I'm saying, oh, look, this is in relation father to son to Y, right? Now, a transitive closure is pretty much you're trying to connect the dots, right? So what is missing? Well, I have to connect all dots to make it complete. So first you need this, right? Because it has to be that Y is a son relation with Z. And then also you need a transitive closure, which makes it transitive. So X is in collection with Z, right? And then you can also make it, I didn't require you to make it, for instance, reflexive, but you could easily do reflexivity by adding these self nodes, right? This will make it reflexive, right? Anything is in relation with itself, right? this won't break transitivity. So both are transitive closures. One is bigger than the other, right? So in the end, I told you take the smaller one, right? So for instance, the first one without the self nodes will be the smaller possible, okay? So yeah, so whenever you think of transitive closure, another way to see it is just trying to connect this graph, okay? And then the key thing about transitivity is that there is no loop, right? Except the reflexivity loop, right? But for the other loops that are not the same loop, there is no loop. For instance, if I create this one here, will this be transitive? Not anymore, right? Because now you have that X is in relation with Z, and now pretty much you have by implication that you have this loop. So this is not this is not a cyclic in this particular case. A cyclicity is more important here. This is a cyclic loop, okay? And that's it. So yeah, so transitivity is is related to having no loops. So this object here is transitive, right? And now you have it. Okay, good. So with that, we're done. I'm gonna stay a little bit more, 10 minutes, 15 minutes more, so people can ask me questions. And in particular, the notes today, I added some material. So I'm gonna update it in a second, right? Let me do one thing. Let's go back to the leaks. Okay, so I added some material, of course. So I'm gonna save it now. And now I'm gonna, of course, upload it to the GitHub. So the GitHub will give you the leaks, the new leaks version. So the compiled version, you can do it using leaks yourselves, right? So there is you may have some conflicts. You can use show output anyway. Anyway, I'm gonna compile these things. For instance, today I'm gonna compile it at the end of the day because I may want to make some additional changes, okay? So pretty much you can expect before the class, there is gonna be a new PDF. So in order to, you don't need to compile this thing. If you want to compile it, you can use leaks and you can do an effort to compile it. It's not gonna be as easy because you need LaTeX and you need a lot of packages and so on. So it's not mandatory that you do it. You can also read it in leaks directly, right? But so if you want to have access to the PDF, I'm gonna do it anyway before the class, right? So you're gonna have access to the compiled by me version. Yeah. Well, so again, so tomorrow, remember, I'm gonna do a video that's gonna be around an hour, a little bit less than that, which is gonna be the material of chapter 2, okay? So then so we're gonna meet tomorrow at 2. I'm gonna send you an announcement. So instead of meeting at 1, we're gonna meet at 2. So the idea is we keep the kind of time constant, but instead of meeting at 1, we're gonna meet at 2 to do this kind of oral exam, right? Which is just like a diagnosis. So I'm not gonna grade you anywhere. I'm gonna tell you feedback, right? It's more about testing the platform. But the main point is that I'm gonna call you some people at random, and then we're gonna discuss. Why I'm doing only 1 hour? Because the first hour is you have pretty much the option to check in the video, right? Which is gonna last more or less 1 hour. So it's gonna be more or less the same, okay? So, and in particular, what is gonna be the problem? So I'm gonna tell you already. So in chapter 2, we're gonna learn about consumer theory, okay? So, and then I'm gonna give you a problem of modeling. So I'm gonna say, oh, look, consider this particular situation. I'm gonna tell you tomorrow, please do a model with these particular features, right? And then you can do it. And the way we're gonna do it, again, is that as we did today. So we can use this board, the InVision. If you don't feel comfortable using it, you can also write it in a piece of paper and then send me a picture of it. Now it's very fast, right? I just can share it. It's gonna be fast. And I'm gonna send you some links of some apps in Android or Apple that takes really, really good scan-like pictures when you take pictures of a piece of paper. So my undergrad students didn't have any issues using that. So I asked them to send kind of pictures and pretty much a PDF of their problems, and they could do it, right? So you use whatever you think is better. And in particular, we're gonna do a lot of these things oral and also gonna write it myself, so it's kind of doing it together. So, but the main thing is read chapter 2 until the subsection. I want you to pretty much until implications of work. So this part of running models versus need, this is the part I want you to read. That's the last part I want you to read. So in other words, or chapter 2, which is very short, it's easy, for tomorrow. I'm also gonna do a quick video of that chapter that I'm gonna upload tomorrow morning, and then you can watch it instead of the first hour. So I'm gonna put all of this in an announcement, but tomorrow we're gonna meet from 2 p.m. to 3 p.m. East, ET, right? And then I'm gonna call you, some of you at random, and then we're gonna do these kind of work groups in these breakout rooms. Okay, so again, you have everything you need now. The notes are on GitHub. You have this, you have also the Zoom link. It's gonna be the same link. You just can join. It's gonna be repetitive until Friday, okay? Reach me out now by email. In between, I'm gonna try to create this as Slack platform so we can chat, but you are free to email me now. And now, yeah, I'm just gonna be here sitting. You can leave if you want, the time is done. But any people that have any questions, any doubts, I can answer, okay? Okay, thank you. Thank you, everyone. Nice to meet you.
So near the end, I think you mentioned the relationship between transitivity and cyclic, I think, cyclic.
Yeah.
I wasn't really clear on that, the last part that you just.
What is the difference between the two?
Yeah. So did you? I wasn't sure. You said if it's cyclic, it's not transitive. Did you say, or?
Yeah. So a cyclic is different than transitivity. First of all, so an example that I gave you in the board, but let's pretty much see it now. So let's share it again and do it quickly. Okay. So in this particular diagram, right, you have, let's study the version with not self nodes, okay? So this version, as simple as this, okay? And I'm gonna study this following thing. So in this case, right, so if I have this node here, the final, this relation here is a cyclic, right? You have X is in relation with Y, and Y is in relation with Z. And then Z is not in relation with X, okay? However, is this relation transitive?
Not yet.
It's not transitive, right?
Oh.
So that's an example. This is a cyclic, but it's not.
Okay.
Okay.
Okay. All right.
Yeah. So the main difference is that transitivity. You have to think of transitivity as being a completed cyclicity, right? So for instance, if I fill in the blanks, right, this is a cyclic, and then I say, look, let's fill in the blanks. So now let's make it so that I will infer, as some of your classmates said, let's interpolate, right? So if I say X is better than Y and Y is better than Z, now X is better than Z, right? Now it's transitive.
Okay.
But it's also cyclic, of course, right?
Oh, it's still cyclic, but also transitive. Okay.
Exactly.
That makes
sense.
Okay.
So that's the difference. So a cyclicity, think of a incomplete version of a transitivity. So transitivity kind of needs completeness to work properly. You can have the two separately, right? But cyclicity is more powerful because it can be stated without any connection to completeness, as you saw from this example, right? So this thing was a cyclic, no loops, but it wasn't transitive. So transitive needs extra edges. Okay.
Okay. Thank you.
So then I'm wondering about the example that we did in class. So there was a father in relation to the son, right?
Yeah.
And that was the relation being the father, and we expanded it to being a family member with the wife of A, right? Would that then not be transitive, because you could have their family members, right? With each other. So like if A is a family member with B and B is a family member with C or X, Y, Z, whatever, then that's transitive. Then X would also be a family member with Z. But could that become cyclical? Because Z,
Great. That's actually a very cool example. Yeah. So transitivity and acyclicity are different. And that's an example where it actually works, right? Because you describe something that is transitive, right?
Mhm.
Because this is a symmetric relation. So symmetric relations are transitive, right? So if you have a family member A is in relation with 2 and 2 with 3, of course, 1 and 3 are related. But at the same time, this is a cycle, right?
Yeah.
So this is an example of transitivity that is actually cyclic. So these things are different. They coincide when the ordering is strict, okay? So for instance, greater than equal, right?
Right.
Greater than equal. Then this is both transitive and acyclic, right? But that's a great point. So transitivity, a case where it fails to be acyclic is when it's also symmetric. So symmetric relations are transitive because, as you can say everyone is on the same family. So this is a symmetric relation, right? It's also transitive, but it's not acyclic, of course, because symmetry is not compatible with acyclicity, right? So they are different objects. They coincide when you have strict preferences or strict relations. And in those cases, usually they coincide like the greater than equal relation, which is acyclic and transitive. So their intersection is not empty, of course, but they are different objects in general. So yeah, great observation.
Okay, thank you.
Yep. Any other question? Also operational things, any concerns? I'm open to it.
Victor, for the fall term, the exams, how would the exams be operated in this class?
Yeah. So again, as you know, everyone is figuring out things, right? So what is for sure is this: I do a midterm and a final. It's only one midterm and a final, right? Problem sets, I'm gonna upload the syllabus. The structure of grades is usually the same. So problem sets counts like very little, is less than 10%. The final is most of the notes, so it's basically 60%, something like that. And then the other is the rest, right? The midterm is the rest. So that means that problem sets actually don't count much. There are more practice for the exams. Midterm also counts less than the final, right? And in general, the final is kind of the most important majority of the grade. Now, this time, because our class is small, right? The exam is gonna be, the midterm at least, is gonna be partly oral examination, right? So not completely, but part of it. So the format is gonna be that I'm gonna have kind of this per student session, right? With some other students as observers, not all the class. You can choose who's the observer, right? And then we can pretty much go through some questions and so on. And the way I'm gonna grade it is half the oral examination, half some task that I'm gonna send you to your as a written task, part take home problem set. I'm not gonna do in-person exams, so everything is gonna be remote, everything, including examinations. Okay, so for me there is nothing that is physical, including exams. Okay, but part of the exams may be oral examinations, and part of the problem set grade and part of the midterm will be this kind of oral quizzes. So part of the process will be split pretty much on take-home exam, assignment, home assignment, and oral quiz. So pretty much the grade of the problems is going to be split into. In general, the main idea of this kind of in-person thing is to try to do more of a flipped classroom. So do more problems in class, and then a lot of the notes and kind of lecture material is going to be half of the class is going to be dedicated to that, and the other is going to be more exercise. Of course, those are going to be connected, so it's pretty much the same sequence. In short, the key thing is that you are going to have 3 sources of points. So problem sets, oral examinations in class, midterm, final. That's it. Yeah, and everything is remote. Everything is remote. Yeah, for all examinations also, we have a clear schedule, so everyone knows, and you cannot do it, we are able to substitute it. So that's going to be, I'm just teaching this class, so I have a lot of flexibility. Yeah, that's basically it.
I just have a question about tomorrow's lecture.
Yep.
So basically, we just review chapter 2, and then you'll go through the material and just ask at random one of us to answer some questions. Is that what you were talking about?
So tomorrow class is going to be, so I'm going to do, instead of a lecture, I'm going to do an hour video. So the idea is going to be how that is, a little bit this week is testing, right? So there are some materials that I think you're going to benefit from having this recorded. Like, this is of course being recorded, but it's going to be more formal and more to the point. And so this is an hour capsule, right, of material of chapter 2. So it's a complement to you reading it. So it's not mandatory that you read it. If you can read the notes and you're done with it, that's it, right? Now, in the second hour, so from 2 to 3, where we're going to meet, synchronize, is to be able to work together on a problem set, right? So I'm going to first solve a problem set myself, pretty much in class. You can see how it goes. And then I'm going to do something related to some people in class, and then some questions about that. So it's going to be more like problem solving tomorrow. So that's the idea, okay? So we're going to have 3 work groups, as I told you in the breakout rooms. And then inside these smaller groups, I'm going to give you 3 assignments, different assignments. And then pretty much there's going to be a person that is the person that is going to be assigned to present the solution to this problem, right? But you can work in the group, and also I will provide help. So it's pretty much kind of do part of the problem set in class. That's it. And so that's going to be very specific to tomorrow. And then I'm going to do another one on Thursday. So the idea is that you have 2 days that we're going to do problem sets in class, so you can familiarize yourself with how is the problem set. Okay. So it's more like testing. So this grade is not going to be anywhere. It's more about trying to understand the format for the main class. Okay, but that's it. So read it, because it's going to be like simulation of what's going to be the main class. So you already know what's going to be happening. Okay.
Victor, will you be in London for the fall semester?
Sorry?
Will you be in London for the fall semester? Like,
yeah, I'm here in London, and again, the in-person, I decided to do it online because of the current situation. So this is gonna be online as well, if that's your question. And so yeah, so I'm doing it is out of a choice. Right now we're close to 0 cases, but we don't know. So I just decided to go online with the probability that I think we're gonna go to lockdown somewhere in between. Yeah, so my class is online completely until something happens. Yep. Now, in terms of trying to do, I'm gonna give you some, as I told you, ways to communicate with me. But also feel free to email me and so on. So the key idea is to try to keep communication open. Okay. Yeah.
So the problem set that we're gonna work during the class, so we won't have access to it before the class, right? We're just gonna be presented during the class. So just work with the classmates basically, and then answer on the spot.
Yeah. So tomorrow is gonna be like that. Other days, like for instance, I think actually reasonable in things that are larger to give you the problem set. But that's a little bit defeats the purpose. So a little bit idea tomorrow is to be able to work with your classmates in the problem, trying to to get this collaboration part going. And so yeah, so the idea is that you don't know in advance, and you have to solve it in class. Okay. And of course, I'm going to be helping you, and you're going to be broken into groups, so okay, we make it more manageable. So for tomorrow, yeah, you are not going to have access to the problem set. In general, when I'm going to send you the take-home assignments, you're not going to require to present them unless it's something that I want to clarify or so on. So usually in that case, you're going to just give me the written assignment, and then it's going to be graded. So not presented. So this is 2 different things, right? So that means that you're going to see the problem on the spot. Okay?
Okay, thank you.
Okay, so any more questions? Else I'm going to finish this session. Okay, thanks.
Bye.
Bye.